Hello viewers. In the last few lectures, I discussed about solid-liquid equilibria, the so-called condensed systems which are characterized by the absence of vapor phase. We covered simple eutectic systems, peritectic systems, solid solutions and so on. Now, it is time for us to change over to liquid vapor systems, which also fall under two component systems, but in these systems solid phase is absent, and we know why we do this. In order to make the investigation simpler and presentation of the results easier, we study solid liquid vapor systems separately, and whenever we want complete information, we try to put them together. In today's lecture, the plan goes like this. We'll start with liquid and liquid gas systems. We'll spend some time on liquid gas systems, although they are not as important as liquid systems. We'll study solubility of gases in liquids, which is related to Henry's law, then Raoult's law, ideal liquid mixtures, PC diagrams of ideal mixtures, based on which we'll talk about isothermal distillation, then TC diagrams of ideal mixtures, which will help us to elaborate on fractional distillation. Let us look at liquid gas and liquid vapor systems. Liquid vapor systems are very important both from theoretical point of view as well as industrial point of view, because they deal with separation and purification problems where we handle tons of liquids and solvents. But it's worthwhile to spend some time in discussing liquid gas systems, which are very similar to liquid vapor systems, and several ideas can be borrowed from liquid gas systems. Solution of gases in liquids. When a solution of a gas in a liquid is considered, it's a simple case of a two-component system. Consider this. If we bring a gas in contact with the liquid, the gas dissolves in the liquid to give a solution. The dissolution continues till the liquid becomes saturated with the gas, when an equilibrium is established between the gas in the gaseous state and the gas that is present in solution. If we apply phase rule to this system, we know that it's a two-component system. There are two phases in equilibrium. Therefore, from the phase rule equation, we get that F is equal to 2. Which are these two degrees of freedom? Of course, temperature and pressure. It tells us that the composition of the solution, in other words, the solubility of the gas in the liquid, depends on temperature and pressure. But we should not forget that the solubility also depends on the nature of both the gas and the liquid concerned. Let us move forward. Now, most gases dissolve in water with the liberation of heat. What does that tell us? Dissolution is an exothermic process. Hence, if we apply Le Chatelier principle, the increase in temperature should result in the decrease in solubility of the gas. It becomes obvious, if we heat a liquid, the gas that is dissolved will get expelled from the solution. And in fact, this method is used for degassing solvents which are used in what are called HPLC solvents. There are of course some exceptions. Hydrogen halides in water, we don't have to look for the reason. Reason is the possibility of a chemical reaction. But then there are other exceptions. Even without a chemical reaction, for example, hydrogen, helium and oxygen in several organic liquids show this exceptional behavior. At a given temperature and pressure, solubility of a number of gases in a liquid generally increases in the order of their ease of liquefaction. We know, of course, from our earlier experience that a gas can be easily liquefied in which the intermolecular forces are very strong. So, hydrogen and helium, being the smallest of the molecules with very low intermolecular force of attraction, show minimum solubility or the lowest solubility among the gases, whereas easily liquefiable gases like ammonia, carbon dioxide, sulfur dioxide show very high solubility. In these cases, definitely there could be a chance of chemical reaction that is taking place between the liquid and the gases. Extensive studies on the solubility of gases and the influence of pressure on this was carried out by Henry, which resulted in what is called Henry's law. According to this law, the mass of a gas dissolved by a given solvent at constant temperature is proportional to the pressure of the gas in equilibrium with the solution. We can put it mathematically like this: W is equal to K into P, where W is the mass of the gas that is dissolved, P the equilibrium pressure, and K the proportionality constant. This is, of course, the historical version of Henry's law. We know it in a different form, as we will see later. Now, if a gas obeys Henry's law, we should get a straight line for a plot of solubility against pressure. Here is an example in which the solubility of HCl in dry benzene is studied at 30 degrees centigrade. You can see the plot. It's very clear that the points fall on a straight line, and we can say that the particular system, that is HCl in dry benzene, obeys Henry's law. So, when chemical reaction takes place between the gas and the solvent, as in the case of HCl, NH3, etc., Henry's law fails to hold if we consider the total solubility of the gases. However, if we make an estimate of the gas that is actually dissolved, that means excluding the one that has reacted, it is possible to apply Henry's law. If the gases dissolve from a mixture, Henry's law can be applied to individual gases. But the modern definition of Henry's law can be obtained if we consider W, the mass of the gas dissolved in unit volume, to be equivalent to concentration, and then if we consider concentration to be proportional to the mole fraction of the dissolved substance, then we get an equation which is the modern version of Henry's law, that is X2 is equal to K prime into P2, or P2 is equal to X2 divided by K prime, where X2 is the mole fraction of the gas, that is the solute in the solution, when the pressure of the gas above the solution is P2. K prime is the proportionality constant, which is related to the constant K that appeared in the historical form of Henry's law. But very important law is the Raoult's law in dealing with liquid vapor systems. The partial vapor pressure of a substance in a mixture is proportional to its mole fraction in the solution and its vapor pressure when it is pure. Hence, the pressure P2 of the solute in equilibrium with the solution, in which the mole fraction of the solute is X2, is given by P2 is equal to X2 into P20, where P20 is the vapor pressure of the pure solute, in this case liquefied gas, at the temperature of the solution. We can make a comparison between the two because they apply to similar systems. Henry's law, we have put it P2 is equal to X2 upon K prime, and Raoult's law, P2 is equal to X2 into P20. So, comparison shows us that the two laws become identical if we put K prime equal to 1 upon P20. So, this condition is approached in a few cases representing what are called ideal solutions of gases in liquids. In an ideal solution of a volatile solute in a volatile solvent, Raoult's law applies both to the solute as well as to the solvent. For such solutions, Henry's law and Raoult's law as applied to the solute may be regarded as identical. But for majority of solution of gases in liquids, however, the behavior is not ideal. And although K prime we get as a constant as per Henry's law, but it is not equal to 1 upon P20 as demanded by Raoult's law. So, we are interested in dealing with mixture of miscible liquids in order to elaborate on liquid vapor equilibria. Consider the mixtures of liquids like ethanol and water, chloroform and acetone. Now, which is the solvent and which is the solute in these cases? Very difficult to label them, because we are always, when we talk about solution, we think in terms of solute and solvent, but in these cases it is not possible to identify them. Therefore, in these cases we simply say that there are two components, one is component A, the other is component B. Such liquid mixtures in equilibrium with their vapors form the liquid vapor systems. There are some equations which are important while dealing with liquid vapor systems, like total pressure P is given by the sum of the partial pressures. That means capital P is equal to PA plus PB, where PA and PB are the partial vapor pressures of component A and B respectively. PA is given by the product of mole fraction of A in the vapor phase into total pressure. Similarly, for PB we can write an equation where the XA prime and XB prime in the equations denote mole fractions of A and B in the vapor phase. Ideal systems are those which obey Raoult's law over the entire range of compositions, right from 0% A to 100% A, or 0% B to 100% B. This is what we get if we take the vapor pressure versus composition plot. This is exactly as per Raoult's law. You have a linear variation in the vapor pressure of B. PB0 is the vapor pressure of pure B. Similarly, PA0 is the vapor pressure of pure A. And you can clearly see in both cases it is a linear variation. Let us look at the total pressure, which is given here in this diagram, which is the sum of the contributions from the two components PA plus PB making the total pressure, and it smoothly varies from PA0 to PB0 in a linear fashion. The example that we have for ideal systems is a mixture of hydrocarbons like benzene and methyl benzene. The very fact that both are hydrocarbons, that means their molecules are structurally similar and are held together by the similar forces in the liquid state. So, that is the condition. If there is some difference, then non-ideality may set in. Remember that there are no really perfectly ideal systems. We can look at Konovalov's rule. Vapor phase in equilibrium with the mixture of volatile liquids is richer in the more volatile component than the liquid phase. That means the composition of the liquid and the vapor are different, and we can take this to our advantage in the process called distillation, in which we convert a liquid into a vapor by increasing the temperature so that the liquid mixture boils, and the liquid gets converted into vapor, and the vapor that is formed is condensed to get a liquid, and definitely the condensed liquid will have a different composition from the starting liquid. It's time for us to look at the phase diagrams of liquid vapor systems, where we take the pressure versus composition for our discussion. This is the phase diagram where we have plotted the pressure versus composition. You can see the vapor pressure of pure A here marked by point A, vapor pressure of pure B is given by point B, and we have the curves marked vaporous and liquidous, and we know how these names come. Liquidous indicates that above this curve only liquid phase is present, and vaporous stands for a situation where below this curve only the system is present in vapor phase. Between these two we have liquid and vapor in equilibrium. Now, we have drawn a line here AB, which is the tie line, which tells us that the composition of the vapor that is in equilibrium with the liquid under the given conditions. We also noted in the diagram the number of degrees of freedom. We have the liquid alone here, for which the number of degrees of freedom is 2. Here at the bottom we have vapor alone, for which F prime is equal to 2, but in between where the two phases are in equilibrium, we have liquid plus vapor, for which F prime is equal to 1. There is only 1 degree of freedom. Now, let us look at the diagram to find out where this can be made use of. You start with the liquid with the composition marked X, for which the number of degrees of freedom is 2. We know that temperature is kept constant, and decrease the pressure. The pressure can be decreased. There is no problem with it because we have 2 degrees of freedom. When we reach point A, the first vapors appear with the composition given by point B. The system becomes a two-phase system. Number of degrees of freedom decreases by 1, which permits us to bring about further decrease in pressure. And as we do that, the vapor composition starts drifting along the line B to B prime. Similarly, the composition of the liquid, which was at point A, starts drifting towards A prime, which is shown by a series of the lines, horizontal lines called tie lines. And when we bring down the pressure to a point B prime here, the vapor composition has shifted from B to B prime, and the liquid composition has shifted from A to A prime. We are left with only traces of liquid. Most of it has vaporized at point B prime, and then further decrease in pressure leads to complete vaporization as we reach point Y. When we reach point Y, the entire liquid is converted into vapor. We have brought about conversion of liquid into vapor without changing the temperature. What we have done? We simply decreased the pressure, whereby vaporization is brought about. That is why the process is called isothermal distillation. But we know that distillation is carried out by heating the liquid to its boiling point at constant pressure, and that is what we are interested in, for which we need to study TC diagrams, which are more useful than PC diagrams. Look at this. This is exactly the mirror image of the PC diagram. Liquid A had higher vapor pressure, therefore it shows a lower boiling point. On the contrary, liquid B had lower vapor pressure, its boiling point is higher than that of A, but diagram remains the same. And you can see one more difference here. At higher temperature, the system is likely to be in the vapor state Therefore, the upper curve here is the vaporous curve and the lower curve is the liquidous curve. And we can call this liquidous curve also as the boiling point curve, because it gives us the boiling point of the liquid mixtures of A and B of various compositions. So, as we change from 100% A to 100% B, the boiling point changes along the line shown by the liquidus. The upper line, on the other hand, gives us the composition of the vapor that is in equilibrium with the liquid at a given temperature. Distillation can better be explained using this diagram, which is the TC diagram. Very similar argument. Instead of keeping temperature constant, we are now keeping pressure constant, generally at 1 atmospheric pressure, and we are plotting temperature versus composition. It's clear. At lower temperature, the system exists as liquid. At higher temperature, it is likely to be in the vapor state. Therefore, we have liquid here, vapor here, and in between the two curves, that is colored region, tells us about the equilibrium between liquid and the vapor. Now, for our discussion, let's start with a liquid of composition X and heat it. When we reach the point A, it starts boiling. The vapors emerge out. The composition of the vapor is given by point B. As I told you, we are permitted to increase the temperature as we are still having 1 degree of freedom in the two phase region, and as we increase the temperature, the composition of the vapor that is emerging slowly readjusts itself and starts moving towards B prime, and the composition of the liquid starts moving towards A prime, and ultimately we reach the point B prime at which most of the liquid is converted into vapor. Traces of liquid is left, which ultimately gets vaporized, and we are left with only vapor. So, in this case, we have brought about conversion of liquid into vapor, but distillation amounts to slightly different thing, where we want to say separate A and B, and for that we can see how it can be done. Now, look at the same liquid mixture starting with composition X. You heat it. When you reach the point A, you can see that the vapors emerge out. The vapors are much richer in the more volatile component, that is the component A, which has lower boiling point, and if you condense this vapor, you get a liquid of this composition which has become richer in A, and vapors that are emerging out from this liquid, if you heat it, will give you the vapors which are still richer in A, and a series of these steps, vaporization and condensation, will ultimately lead you to pure A. So, it is possible to bring about distillation in a stepwise manner. So, what you are doing? You are vaporizing it, condensing it, vaporizing it and condensing it, and ultimately you get the vapors that are pure A. We have brought about a separation, and this process is called fractional distillation, because we are doing it collecting the fraction and redistilling it, and collecting the fraction and redistilling it till we get the pure liquid A. Fractional distillation involves a series of distillation steps. This diagram illustrates that exactly. We can see in this diagram what we have plotted. We have plotted Xb, the mole fraction of component B in the liquid phase, versus Xb prime, the mole fraction of the same component B in the vapor phase. You start with a liquid mixture that is having a particular composition which is given by point A. When you heat it, you get a vapor having a composition A prime. You can see that vapor has become richer in B, and if you condense this vapor, the diagonal gives us the composition of the liquid that is expected, and the liquid has now become richer in B and you can heat it. That means you are bringing about vaporization, and similarly condensation, vaporization, condensation, vaporization and condensation. That means 1, 2, 3, 4, 5, 6 steps. If you carry out vaporization, condensation, you will get pure B. So, one distillation step is vaporization and condensation as shown in a diagram here, and you are carrying out the same thing stepwise here in order to purify. The distillation apparatus is simple here. You have the liquid taken in the flask, you heat it, it vaporizes, vapors condense here. The less volatile component condense first and start trickling down, whereas more volatile component goes up and ultimately emerges out of the condenser and collected as distillate. But this is what we do in the laboratory scale. But on an industrial scale, we use what are called bubble cap fractional distillation columns, big towers in which you have a series of plates provided with bubble caps through which the vapor rises, and there are overflow pipes through which the liquid trickles down to the lower plates. You feed the liquid mixture somewhere in between, and as the liquid that is present here is heated, the vapors will be rising up, the condensed liquid will be trickling down. What you are actually bringing about? An intermingling of the vapors that are rising and the condensed liquid that is coming down, so that a condition very similar to the equilibrium that exists can be achieved. So that what you get is the vapors that rise tries to vaporize the more volatile component from the liquid that trickles down, and the liquid on the other hand tries to condense the less volatile component and takes it down. Ultimately, the less volatile component starts collecting at the bottom, whereas more volatile component rises to the top and can exit as vapors, which can be condensed as the distillate. So, from the bottom you have high boiling liquid, from the top low boiling liquid, which can be collected as distillate. Here is an enlarged view. You can see these bubble caps. The vapors rise through this, they bubble through the liquid that is condensed on the plate. These are shallow liquid layers here, so that the rising vapors are stripped off the less volatile component. So, the vapors that are now more volatile will rise to the next higher plate and then make their journey upwards. Similarly, the liquid that is collected or condensed on the plates trickle down to the lower plate, and subsequently they reach at the bottom. As they move down, they become richer in the less volatile component or high boiling liquid. That is how a column works, distillation column works on an industrial scale. There are various designs, of course. To improve the quality of the distillate, we carry out what is called reflux. A small fraction of the distillate is returned to the column at appropriate level, which is called the reflux. Higher the proportion of the reflux that is returned to the column, the better will be the quality of the final distillate. That is our aim. We want to see that the liquid that is emerging out as the distillate is in the pure form. In order to define the efficiency of the distillation column, we have two terms. One, the number of theoretical plates n. Higher the number of theoretical plates, the better will be the efficiency of the column. And in practice, as seen earlier in the diagram, the column should have slightly more number of theoretical plates than calculated from theory. You have seen 1, 2, 3, 4, how many steps are required? 6 steps, 7 steps are there. In such a case, you have to have a column which has more number of steps than given by the theory. The other way to express the efficiency is in terms of HETP, height equivalent to the theoretical plate. HETP is the length of the column from the top of which emerges the vapor that is in phase equilibrium with the liquid that leaves from the bottom. The smaller the HETP, the better will be the efficiency of the column. That is how at the industrial scale you can bring about separation and purification of liquid mixtures. Let me summarize what we looked at today. We found out our earlier experience on the phase equilibria. Then we started with liquid-liquid and liquid-gas systems, in which we discussed about solubility of gases in liquids. We looked at Henry's law, Rolle's law, ideal liquid mixtures, PC diagrams and the usefulness of it in explaining isothermal distillation, and then more useful TC diagrams where we could explain clearly what is meant by fractional distillation, and in the laboratory and the industrial scale the type of instrument that we use or assembly that we use to bring about fractional distillation. In my next lecture, I will discuss about systems in which the liquids are partially miscible liquids, and also it is very interesting to look at systems of immiscible liquid pairs. Let us find out why they are important in the next lecture. Thank you.